Welcome to Bedtime Astronomy. Explore the wonders of the cosmos with our soothing Bedtime Astronomy podcast. Each episode offers a gentle journey through the stars, planets, and beyond, perfect for unwinding after a long day. Let's travel through the mysteries of the universe as you drift off into a peaceful slumber under the night sky.
So I want you to just imagine for a second, standing outside on a perfectly clear, incredibly dark night. You are looking up at the sky, tracing those familiar constellations, maybe even spotting a galaxy like Andromeda as this faint, fuzzy smudge against the black.
Right, just a quiet night under the stars.
Exactly. But now I want you to imagine that within one of those distant, quiet galaxies, a star dies. And this isn't your standard stellar death. I want you to picture a detonation so inconceivably bright that it outshines normal supernovae by a factor of 10, maybe even 100.
Oh, easily 100 in some cases, yeah.
Yeah, and it is so luminous that for a brief window in cosmic time, it completely dominates the night sky of its host galaxy, literally outshining billions of other mature stars combined.
It's honestly a scale of energy release that operates at the absolute edge of physical laws. I mean, when we discuss these specific events, we're looking at something that fundamentally rewrites the thermodynamics and really the geometry of its surrounding neighborhood.
It's just mind-bending. And today, our mission is to solve a 16-year-old cosmic cold case. We are going to witness the birth of a terrifyingly powerful stellar engine called a magnetar and discover how a century-old theory by Albert Einstein provided the ultimate key to understanding a billion-light-year distant explosion.
It really is one of the most baffling mysteries of the 21st century.
It really is. Okay, let's unpack this. Because since they were first identified in the early 2000s, these ultra-bright explosions, what astronomers call superluminous supernovae, have been a massive thorn in the side of stellar physicists.
A huge thorn. They completely defied the standard energy budget,
Right. The core anomaly is basically this. Why do these specific explosions stay so intensely bright for so long, well after the star's nuclear fuel is gone and that initial kinetic shockwave has just dissipated?
Exactly. The established mechanics of core collapse simply could not account for the sheer duration and the intensity of that lingering light. I mean, it was as if someone had pulled the plug on a massive city grid, but instead of the lights fading out, the entire infrastructure just kept glowing at maximum intensity for months.
Which makes no sense. So to really grasp why superluminous supernovae broke the energy models in the early 2000s, we have to look closely at the math of a stellar explosion. I think most of you listening are already familiar with the baseline physics, right? A massive star hits the iron limit, fusion stops, gravity wins, the core collapses into a neutron star or a black hole, and the rebound shockwave blasts the outer layers into space.
That is the standard mechanism, yes.
Right, and we know that the lingering glow of a normal supernova is primarily powered by the radioactive decay of heavy elements synthesized in that blast, specifically nickel-56 decaying into cobalt-56 and then into iron-56.
Yeah, and we can calculate exactly how much light a given mass of nickel-56 will produce as it decays. It's very well understood.
Because it's just radioactive half-life, right?
Precisely. A typical core collapse supernova might forge, say, a fraction of a solar mass of nickel-56, which gives you a very predictable light curve. The light rises as the ejecta expands and becomes transparent enough for the trapped radiation to escape. It hits a peak, and then
it fades but smoothly.
Right. It follows a very smooth, mathematically precise exponential decline dictated by the half-life of those isotopes.
But wait. If we see a superluminous supernova that is 10 times brighter, couldn't the simple explanation just be that, well, the star was exceptionally massive and therefore it just forged 10 times as much nickel-56 during the explosion? Like, why did astrophysicists immediately assume there was a mystery to solve?
It comes down to the fundamental limits of nucleosynthesis. To power the light curves we were seeing in these superluminous events, especially the hydrogen-poor ones, known as type I superluminous supernovae, you would need to synthesize an absurd amount of nickel-56.
How absurd are we talking?
In some cases, the calculation showed you would need 5, maybe even 10 solar masses of pure radioactive nickel.
Wait, really? Let me stop you there, because the sheer physics of that seems impossible. You're saying the math required the star to produce more nickel than the entire mass of the core that collapsed in the first place.
That is the exact core of the issue, yeah. A collapsing star simply cannot convert that much of its mass into nickel-56. The thermodynamics don't allow for it.
Right. It would just blow itself apart.
Exactly. The core would become unstable, And pair instability might rip the star apart entirely in a different kind of explosion, but it wouldn't leave the remnants we were observing. So you have a light curve peaking at 10 to the 44 ergs per second, staying there for 100 days, and the radioactive decay model completely fails to provide that energy.
Because you cannot get something from nothing.
No, you can't. The initial shock wave is gone. The radioactive decay is entirely insufficient. Therefore, something else must be pumping extra energy into the expanding debris field.
I was trying to visualize the mechanics of this, and I want you, the listener, to picture the setup. If the fuel is gone, how is the fire still burning? Imagine you have a heavy-duty flashlight. You switch it on, it's blindingly bright. Then you take the battery pack completely out. But instead of the light going dark, the bulb suddenly shines 10 times brighter and stays that way for months.
That is a great analogy.
You would immediately realize there has to be a hidden power source somewhere in the circuitry that you just can't see, right? There has to be a secondary battery.
And that is exactly where the astrophysics community landed. They deduced that the initial collapse and explosion could not be the end of the stellar death process. The only viable explanation for a superluminous supernova was the existence of a hidden engine.
A hidden engine.
Yeah, something active, buried deep within the expanding cloud of stellar debris, continuously injecting vast amounts of kinetic or electromagnetic energy into the wreckage.
But finding that engine is a logistical nightmare, right? I mean, the debris field of a supernova isn't just a wisp of smoke. You are looking at several solar masses of plasma and heavy elements expanding outward at 10,000 kilometers per second. It is optically thick. It is completely opaque.
It is much denser than any material we interact with on a daily basis. The photons generated at the center, they take weeks just to scatter their way out through the expanding ejecta.
Like bouncing around inside a pinball machine.
Exactly, a process governed by radiative diffusion.
Yeah.
So whatever this hidden engine was, it was entirely obscured from our telescopes. We could measure the effect of the engine, that sustained, unnatural luminosity, but we couldn't peer through the glowing plasma curtain to see the machinery actually operating at the center.
So it's basically a locked room mystery, but the room is 1 billion light years across, filled with superheated plasma and exploding.
A very chaotic, locked room. Yeah.
Right. So to figure out what this hidden engine actually was, we have to rewind the timeline to a bold theoretical prediction made back in 2010.
Yes. In 2010, Dan Kossin, a theoretical astrophysicist at UC Berkeley, along with Lars Bilston, put forward a very specific hydrodynamic model. And this concept was actually being developed independently and concurrently by Stanford Woosley at UC Santa Cruz.
Right. Great minds thinking alike.
Exactly. They looked at the energy deficit of these superluminous supernovae and hypothesized that the core of the star hadn't just collapsed into a standard, quiet neutron star. They proposed that the core collapse had birthed something far more extreme, which is a magnetar.
A magnetar. Okay, we know that when a massive star's core collapses, if it doesn't cross the Tolman-Oppenheimer-Volkoff mass limit to become a black hole, it becomes a neutron star. Basically a sphere of degenerate neutron matter.
Right.
But Kazin, Bilston, and Woosley were talking about a very specific, rare subclass of neutron star. Let's break down the anatomy of this monster, because the physical parameters required by their 2010 model are just staggering.
They really are. So to understand the extreme nature of a magnetar, you first have to look at the baseline of a standard neutron star. When that iron core collapses, gravity is so intense that it overcomes electron degeneracy pressure. It literally crushes electrons and protons together to form neutrons.
Just mashing them into a paste?
Pretty much. An entire stellar core, roughly the mass of our sun, gets compressed into a sphere with a radius of only about 10 to 12 kilometers.
So 10 miles across. I want you to really picture that density. You could fit it inside the city limits of most major metropolitan areas, but it contains the mass of an entire sun. Like a single sugar cube-sized chunk of this material would weigh hundreds of billions of tons on Earth.
The density is analogous to the nucleus of an atom, just scaled up to the size of a city. Now, because of the conservation of angular momentum, the classic figure skater pulling their arms in to spin faster, that incredibly dense sphere is going to be rotating.
Right. It speeds up as it shrinks.
Exactly. Most newborn neutron stars spin quite fast, maybe a few dozen times a second, and they possess strong magnetic fields. We observe those as pulsars.
But a magnetar takes those parameters and dials them up to an almost incomprehensible degree. How does a standard neutron star become a magnetar during that initial collapse?
It requires a perfect storm of initial conditions. The progenitor star likely needs to have a rapidly rotating core and a pre-existing magnetic field. During the split second of the core collapse, you have incredibly violent convection currents churning inside the protoneutron star.
It's boiling inside.
Right, boiling violently. And if the rotation is fast enough, those convective currents combine with the rotation to create a runaway dynamo effect.
Yeah.
This dynamo amplifies the magnetic field exponentially before the star even has a chance to fully cool and settle.
Wow.
So instead of a standard pulsar with a magnetic field of, say, 10 to the 12 Gauss, which is already billions of times stronger than Earth, you get a magnetar. A magnetar's magnetic field operates in the range of 10 to the 14 to the 10 to the 15 Gauss.
That is insane.
It is 100 to 1,000 times stronger than a typical pulsar.
I don't think the human brain is wired to intuitively understand a magnetic field of 10 to the 15 Gauss.
Yeah.
If you were somehow able to survive the radiation and approach within 1,000 miles of a magnetar, what does a magnetic field of that magnitude physically do to ordinary matter? Like, to a person?
It entirely overrides the electromagnetic forces that hold matter together. A field that's strong physically warps the electron orbitals of atoms. Instead of spherical electron clouds, the magnetic field stretches the atoms into long, thin, needle-like cylinders.
Needles. That sounds horrifying.
It would completely dissolve the molecular bonds of your body.
Yeah.
The chemistry that makes life or even solid objects possible just ceases to function. The magnetic field becomes a dominant physical force, rivaling gravity and the strong nuclear force in the immediate vicinity of the crust.
Okay, so Kaysen's 2010 model places this 10-mile-wide ball of ultra-dense matter-warping neutrons at the center of the supernova. But a strong magnetic field alone doesn't generate light, right? To power the supernova, this magnetar has to be moving. How fast did their math require this object to spin to account for the energy deficit we talked about earlier?
To match the luminosity of the brightest supernovae, the 2010 models required the newborn magnetar to be spinning at near breakup velocity. We're talking about rotational periods of 1 to 5 milliseconds.
Milliseconds.
Yes. That means this city-sized object is completing a full rotation roughly 1,000 times every single second.
Let's just push on that for a second. An object with the mass of a sun spinning 1,000 times a second. The equator is moving at a significant fraction of the speed of light. The centrifugal forces trying to rip the star apart must be fighting a titanic war against its own gravity.
And gravity only barely wins. But it's exactly that tension, that immense reservoir of rotational kinetic energy that serves as the hidden engine.
Ah, I see.
Here is how the mechanism actually powers the supernova. You have this newly formed magnetar at the exact center of the expanding debris field. It is spinning 1,000 times a second. As it rotates, that 10 to the 15 Gauss magnetic field whips around with it.
So you have a magnetic field tearing through the immediate surrounding space at relativistic speeds.
Yes, and a rotating magnetic field generates an intense electric field. This extracts charged particles from the surface of the neutron star and accelerates them to near the speed of light, creating this massive outflow of energy called a pulsar wind.
Oh, wow.
And this highly energized wind of particles and radiation just slams violently into the inner wall of the expanding supernova ejecta.
So instead of the debris field just expanding outward and, cooling adiabatically into the dark, it is constantly being superheated from the inside by this relativistic particle wind.
That is the precise mechanism. The continuous injection of energy from the magnetar's wind heats the surrounding plasma. This process, known as magnetic dipole radiation, converts the rotational spin energy of the neutron star into thermal energy in the ejecta. This is what keeps the plasma glowing white-hot, entirely solving that energy deficit problem.
Incredible.
The magnetar basically acts as an unseen dynamo, slowly spinning down over weeks and months, transferring its rotational energy into the light we see.
But wait, I have a question about the timeline here. If you have a magnetic field that is 100 to 1,000 times stronger than a normal pulsar, the magnetic braking effect must be immense. Doesn't that intense field act like a massive friction brake, causing the magnetar to spin down and lose its energy almost immediately? How does it sustain the glow for hundreds of days?
That is a fantastic point, and it's exactly why the math works so perfectly for a superluminous supernovae. You are right, magnetic braking is severe. A normal pulsar might spin for millions of years. But a magnetar, because its field is so strong, sheds its rotational energy very quickly. The spin-down timescale for a magnetar with a millisecond period and a 10 to the 14 Gauss field is on the order of weeks to months.
Oh, and weeks to months is exactly the duration of a superluminous supernova light curve.
Yes. The rate at which the magnetar hits the brakes and dumps its energy perfectly matches the timescale required to keep the supernova bright. If it's spun down in seconds, you just get a brief gamma ray burst. If it spun down over centuries, the energy injection would be too slow to outshine a normal supernova. The magnetar hits the absolute physical sweet spot.
It is just a breathtakingly elegant theory.
What's fascinating here is how Dan Kazan viewed his own model. He noted that for years, this magnetar engine concept felt almost like a theorist's magic trick.
Because they were essentially inventing an invisible machine just to balance their equations.
To a degree, yes. It was mathematically robust, but observationally frustrating. Theorists were essentially saying, we have this giant, unexplained luminosity. We will solve it by hiding a phenomenally powerful, totally unobservable engine behind the thickest layers of stellar debris in the universe.
Very convenient.
Right. It's a highly natural explanation, but because the ejecta is so optically thick, thanks to Thomson's scattering of photons off free electrons in the plasma, there was no direct way to look inside and verify the engine's existence.
So they were staring at the glowing curtain, mathematically proving that a wizard must be pulling the levers behind it, but unable to actually open the curtain.
Exactly.
And in astrophysics, a beautiful mathematical model is just a theory until the universe gives you proof. They had to wait 16 years for that proof. The theory was published in 2010, and the definitive proof finally arrived in December 2024.
It did.
But when it did, it didn't just give us a blurry glimpse of the engine, it laid bare the exact mechanical workings of the magic trick.
It really did. Yeah. And the data came from a very specific, highly unusual stellar explosion designated SN 2024-FAV.
Let's look at the observational logistics of SN 2024-FAV, because the scale is staggering. This event wasn't happening in our galactic neighborhood. The host galaxy for this supernova is located approximately 1 billion light-years from Earth.
To put that immense distance into context, the photons we analyzed from SN 2024-FAV began their journey across the universe 1 billion years ago. Long before the first multicellular organisms even evolved in Earth's oceans, this massive star exhausted its fuel and collapsed.
That is just awe-inspiring to think about.
It is. That light traveled through the expanding vacuum of intergalactic space, completely undisturbed, until it finally struck the mirrors of our telescopes in late 2024.
And astronomers were uniquely prepared to catch it, thanks to the Las Cumbres Observatory. For those who aren't familiar, Las Cumbres isn't just a single telescope on a mountain. It is a globally distributed, interconnected network of robotic telescopes. They have 27 instruments placed strategically across different longitudes and hemispheres.
The geographic distribution is the key to their success. Historically, if you wanted to monitor a supernova, you were limited by the Earth's rotation. The sun comes up, your observation window closes, and you have to wait for nightfall.
And in that 12-hour gap, crucial data could be lost.
Exactly. Furthermore, you are at the mercy of local weather. If it rains for a week, you miss a massive chunk of the light curve.
But with Las Cumbres, the sun never rises on their network.
Precisely. As dawn approaches a telescope in Hawaii, the system automatically hands off the observation to a telescope in Australia, and then to South Africa, and then to Chile. It provides continuous, unbroken surveillance of a target. They can stare at a single point in the sky relentlessly. And for SN 2024-FAV, they tracked it continuously for more than 200 days.
That continuous cadence is what cracked the case, because when you map out the brightness over time, creating that light curve, you need high-resolution data to spot anomalies.
Right, you need to see every little dip and spike.
Yeah, and for the first month and a half, SN 2024-FAV looked like a fairly standard, though extremely bright, superluminous supernova. It surged in brightness, hit its peak luminosity, and started its long, slow decline. But then about 50 days after peak brightness, the data did something bizarre.
Graduate student Joseph Farah, operating out of UC Santa Barbara and the Las Cumbres Observatory, along with senior astronomer Andy Howell, they were analyzing the photometric data. And they noticed that the fading light curve wasn't smooth. The exponential decay was being interrupted.
It wasn't just a gentle slope downward.
No, it wasn't. Instead of steadily fading, the luminosity of the explosion suddenly spiked, reached a mini peak, and then fell back down. And then a few weeks later, it spiked again, peaked, and fell. It repeated this pattern, creating highly distinct, measurable bumps in the light curve.
Okay, I want to push on the data quality here. When you are looking at a signal from 1 billion light years away, the signal-to-noise ratio has to be challenging. How did they know these bumps weren't just instrumental errors or atmospheric interference or just, noise in the CCD cameras?
The Las Cumbres pipeline is incredibly rigorous about characterizing noise. Because they have multiple telescopes observing the same event, they can cross-correlate.
Oh, that makes sense.
Right. If a telescope in Chile sees a bump, but a telescope in Australia observing at the same time doesn't, it's a local artifact.
Yeah.
But these bumps were consistent across the entire network. They were statistically robust, high sigma deviations from the expected decay curve. The supernova was physically flashing brighter.
And looking at the data, they didn't just record one or two flashes. They recorded 4 distinct bumps in the light curve over a period of several weeks. Now, the absolute key to unlocking this mystery lies in the timing of those 4 bumps. I want you to visualize the spacing. The time interval between the first bump and the second bump was a certain number of days, but the time between the second and third bump was noticeably shorter.
Yes.
And the time between the third and fourth bump was shorter still. The intervals between the brightness spikes were progressively decreasing.
The frequency of the fluctuations was accelerating.
Joseph Farah used a brilliant analogy to describe this accelerating frequency. He compared the pattern to the rising pitch of a bird's chirp. If you imagine a bird calling tweet, 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 the notes get closer together and higher in pitch at the end.
It's a very evocative way to put it.
Yeah, that exact accelerating rhythm was embedded in the photonic data from 1 billion light years away. But let's look at the historical context here, because seeing bumps in a light curve isn't entirely unprecedented, is it? We have observed supernovae with jagged light curves before.
We have. It is relatively rare, but astronomers have documented supernovae that show 1 or 2 spikes in brightness as they fade. However, the astrophysics community had a very well-established standard hydrodynamic explanation for those events.
They attributed it to circumstellar interaction, right? The shock wave hitting pre-existing gas.
Yes, exactly. Dying massive stars are highly unstable in the millennia leading up to their death. They experience violent mass loss episodes, essentially ejecting massive shells of gas and dust that form a thick, complex nebula around the star. When the star finally undergoes core collapse, the supernova ejecta expands outward at a significant fraction of the speed of light, and eventually it slams into those pre-existing shells of circumstellar material.
Ah, like a high-speed snowplow crashing into a dense snowbank.
That's a great way to picture it. When the fast-moving ejecta hits the slow-moving gas shell, a massive forward and reverse shockwaves is generated. The kinetic energy of that collision is violently converted into thermal energy in X-rays, which get reprocessed into optical light.
Got it.
That collision registers as a distinct bump on the light curve. So, historically, when astronomers saw a bump, the default assumption was simply the supernova debris just plowed into a dense pocket of gas.
But wait, previous supernovae have shown 1 or 2 light bumps from shock waves hitting surrounding gas, so why is 4 bumps such a paradigm-shifting deal? Like, if a star can burp out 1 shell of gas, why couldn't it burp out 4 shells of gas, spaced perfectly so the shock wave hits them one after another?
When you look closely at the fluid dynamics, the circumstellar interaction model completely breaks down for this specific light curve. First, as you noted, the shells would have to be perfectly spaced to create an accelerating rhythm, which is highly improbable in nature.
Right. Space isn't usually that neat.
Exactly. But more importantly, the physics of the collision itself precludes this kind of signal. When the ejecta hits the first shell of gas, it doesn't just pass through cleanly. The collision creates severe Rayleigh-Taylor instabilities. The boundary layer becomes incredibly turbulent and chaotic.
So the expanding shock wave gets shredded and smeared out.
Yes. By the time the ejecta passes through the first shell and hits a hypothetical second or third shell, the shock front is no longer a sharp, distinct wall. It is a messy, turbulent transition zone. You wouldn't get sharp, distinct, individual flashes of light. The collisions would blend together into a broad, messy plateau of sustained brightness.
The structural integrity of the shock wave is gone.
Yes. The sheer number of bumps, their sharp profile, and most crucially, that very specific accelerating chirp rhythm entirely ruled out random collisions with surrounding gas clouds. Random fluid dynamics do not produce highly structured, mathematically accelerating rhythmic flashes.
Wow. Okay.
When Farah and Howell analyzed this data, they realized the universe was signaling something deeply mechanical. Something rotating, geometric, and structured was operating at the core of the debris field.
The hidden engine was finally revealing itself. But, realizing it was an engine and understanding how it worked are 2 very different things. To decode the specific accelerating chirp of SN 2024 FOV, Farah's team had to abandon classical Newtonian physics entirely.
We did.
They realized that standard gravity and hydrodynamics couldn't explain the rhythm. They had to utilize Albert Einstein's theory of general relativity.
This is where the physics gets truly profound. To understand the mechanism, we have to look at the immediate aftermath of the magnetar's birth. The star's core is collapsed, the magnetar is spinning furiously, and the outer layers of the star have been blasted outward.
Right.
But the explosion isn't perfectly efficient. Gravity is still an overwhelmingly dominant force in the immediate vicinity of the newborn neutron star. So a small fraction of the innermost stellar material doesn't reach escape velocity. It gets caught in the magnetar's gravitational well and begins to fall back inward.
Oh, this is the fallback accretion phase.
Yeah.
But the material doesn't just drop straight down onto the surface, right? Because the star was rotating before it died, the exploding material still carries angular momentum.
Right, conservation of angular momentum dictates that the infalling material must swirl. As it falls back toward the magnetar, centrifugal forces cause it to flatten out into a superheated, extremely dense ring of plasma orbiting the equator of the neutron star.
An accretion disk.
Yes, this is an accretion disk. So the architecture of our engine is a central, hyperspinning magnetar surrounded by a flat disk of glowing, swirling plasma.
But the critical geometric detail here is the alignment. The accretion disk is not perfectly aligned with the magnetar's equator, is it?
It is highly unlikely to be aligned. Core collapse supernovae are inherently chaotic, asymmetric events. The neutrino heating that drives the explosion is turbulent. Often, the neutron star itself receives a massive kick velocity during birth due to these asymmetries, completely skewing its rotational axis.
So it's slightly off-kilter.
Right. Therefore, the angular momentum vector of the fallback material will almost certainly differ from the spin axis of the newborn magnetar. The accretion disk forms at a tilt. It is misaligned relative to the magnetar.
I want to make sure I'm visualizing this correctly. You have the magnetar spinning on its vertical axis, straight up and down like a top. But the accretion disk of superheated plasma circling it is tilted at a sharp angle, like a hula hoop that has been tipped partially over.
That is the exact geometry. Now, if we lived in a purely Newtonian universe, classical physics says that tilted disk would simply maintain its orbit. The gravity of the central mass would hold it in place, and it would just spin at an angle indefinitely.
Just happily spinning along.
Right. But a magnetar does not exist in a classical Newtonian framework. It is an object of extreme mass and density, spinning at a significant fraction of the speed of light. And this is where Einstein's general relativity takes over.
Because Einstein proved that space is not just an empty coordinate system. It is a physical fabric. It has geometry. The stress-energy tensor tells us that mass bends the fabric of space-time, creating what we perceive as gravity.
Mass tells space-time how to curve, and curved space-time tells mass how to move. That is the foundational concept of general relativity.
Classic Einstein.
Exactly. But Einstein's equations reveal a secondary, even more bizarre effect. If a massive object is strictly stationary, it just creates a static dimple in space-time. But if that massive object is rotating, it doesn't just bend the fabric, it physically drags the fabric of space-time along with it as it turns.
Wow.
This phenomenon is known as lens-through precession, or more commonly, frame dragging.
Frame dragging. It is a concept that just challenges our basic intuition of reality. The best way I've found to conceptualize this, and I want you to picture this at home. Imagine a large jar filled with incredibly thick honey. If you take a spoon, push it right into the center of the honey, and just hold it still, the honey wraps around the spoon but remains stationary.
Yeah, a static dimple.
Yeah, that represents a static mass bending space. But if you take that spoon and start spinning it incredibly fast, you don't just rotate the spoon. The friction grabs the honey itself, and the honey gets dragged into a swirling, twisting vortex around the spoon.
That is a phenomenal analogy for frame dragging. In this astrophysical scenario, the spinning spoon is the newborn magnetar, and the thick honey is the fundamental metric of space and time itself. The magnetar is spinning so furiously and contains so much concentrated mass that it is literally twisting the geometry of the universe around it in a cosmic vortex.
So the local space-time around the magnetar is physically swirling. But how does dragging space-time create a flashing light? Like, how does that vortex explain the 4 distinct bumps we saw in the Las Cumbres data?
We have to bring the tilted accretion disk back into the picture for that. That tipped-over hula hoop of plasma is physically embedded inside that swirling vortex of space-time. As the fabric of space is violently dragged around the magnetar, it exerts a profound gravitational torque on the misaligned disk.
Oh, because the space itself is moving.
Yes. The disk has no choice but to follow the curvature of the space it occupies. The twisting space-time violently yanks on the disk, causing the entire structure to wobble.
Wobble in the same way a spinning top behaves as it starts to lose momentum. You know, the way the axis of the top starts tracing a slow circle in the air.
Exactly. In orbital mechanics, that wobble is called nodal precession. The entire tilted disk is precessing around the magnetar's spin axis. Now think about the optical layout of this system. At the center, you have a boundary layer where the disk meets the magnetar, which is generating immense amounts of high-energy radiation X-rays and extreme ultraviolet light.
Super bright.
Yes, intensely bright. And surrounding that brilliant center, you have the thick, opaque, tilted disk of plasma, which is now wobbling in a circle due to frame dragging.
Oh, I see it. The wobbling disk acts like a giant physical shutter.
Precisely. It creates a cosmic lighthouse effect. As the tilted disk wobbles, its geometric orientation relative to our line of sight on Earth is constantly shifting. During one phase of the wobble, the thickest part of the tilted disk rotates into our line of sight, physically blocking the intensely bright central emission region. The supernova appears slightly dimmer to our telescopes because the core is obscured.
But the space-time vortex continues to drag the disk, forcing the wobble to continue.
And half a precessional cycle later, the disk tips out of the way. Our line of sight to the brilliant superheated central region is clear, and a massive pulse of radiation escapes toward Earth. Additionally, the broad face of the tilted disk can act like a mirror, catching the intense radiation from the magnetar and reflecting a massive pulse of light outward.
So it's unblocking it and reflecting it.
Yes, and regardless of whether it's unobscuring the core or reflecting light, the observational result is identical. A sudden, massive spike in luminosity.
A bump in the light curve. One full wobble of the accretion disk produces one distinct pulse of light. It's a lighthouse driven not by a mechanical motor, but by the physical warping of space-time itself. That beautifully explains the flashing. It explains why the bumps exist, but we still have to address the chirp. The time between the bumps was shrinking, the frequency of the flashing was accelerating. How does the lens-throwing wobble explain the acceleration?
It explains it perfectly when you consider the thermodynamics of the disk. An accretion disk is not a static ring. The plasma within the disk is subject to magnetorotational instabilities and extreme friction. As the gas particles rub against each other, they generate heat and radiate energy away.
Right, they're losing energy.
Exactly. By shedding this orbital energy, the material loses angular momentum and slowly spirals inward, falling closer and closer to the surface of the spinning magnetar.
And if we go back to our honey analogy, what happens as you move closer to the spinning spoon?
The vortex becomes exponentially stronger. The frame dragging effect, the twisting of the space-time metric, is inversely proportional to the cube of the radius. It gets significantly more violent the closer you get to the surface of the neutron star. So as the accretion disk loses energy, shrinks and spirals inward, it moves into regions of space-time that are being dragged much more rapidly.
Which means the gravitational torque on the disk increases dramatically.
Yes. Stronger dragging produces greater torque, which forces the disk to precess, or wobble, faster. As the disk spirals inward over a period of weeks, its precessional wobble continuously speeds up. A faster wobble means the disk is acting as a shutter more rapidly, blocking and reeling the central light at an accelerating pace.
Faster wobble equals faster flashing. The time interval between the light pulses naturally gets shorter and shorter.
That is the origin of the chirp. The viscous inward spiral of a tilted disk inside a frame-dragging vortex perfectly dictates the accelerating rhythm seen in the Las Cumbres data. If we connect this to the bigger picture, the profound achievement here is that Farah's team didn't just propose this as a neat qualitative idea. They took the exact field equations of general relativity, calculated the theoretical precessional rate of an inspiraling disk around a rapidly rotating mass, and plotted that mathematical curve over the observational data from SN 2024 FAV.
Let me guess, it fit.
The relativistic model mapped perfectly onto the four bumps.
The math of Einstein's spacetime dragging exactly matched the real-world flashes arriving from 1 billion light-years away down to the statistical noise limit.
It was an impeccable fit.
Yeah.
And its significance cannot be overstated. This is the very first time in the history of astronomy that general relativity has been strictly observationally required to explain the mechanics of a supernova light curve.
Really? The first time?
Yes. We use relativity constantly for black hole mergers, for gravitational waves, for cosmological expansion, but supernovae have historically been the domain of Newtonian physics, hydrodynamics, and nuclear physics. This event unequivocally demonstrated that you cannot understand the death of this specific star without evoking the severe relativistic warping of spacetime at its core.
The elegance of that is just breathtaking. But I want to push back again, because the scientific method demands skepticism, right? When you claim to have found a relativistic spacetime vortex powering a supernova, you don't just publish and call it a day. You have to actively try to break your own model. You have to search for a simpler, less exotic explanation. How aggressively did the research team test alternative physical models before concluding that Einstein was the only answer?
Oh, they attack their own data relentlessly. Occam's razor dictates that you must exhaust all classical explanations before invoking general relativity. The team spent months throwing every alternative torque mechanism they could think of at the data to see if anything else could produce that specific wobble.
What other forces could conceivably cause an accretion disk to precess?
They initially looked at purely Newtonian effects. For example, if the central neutron star was slightly oblate, meaning squashed at the poles due to its rapid rotation, its classical gravity would be asymmetrical. Could that equatorial bulge exert a classical gravitational torque and cause the disk to wobble?
That seems like a very reasonable, non-relativistic hypothesis.
It is entirely reasonable. But when they ran the calculations, classical Newtonian precession scales differently with the radius of the disk compared to relativistic precession. The math showed that while the Newtonian bulge would cause a wobble, it would not produce the specific accelerating rate of the chirp they observed. It couldn't match the timing.
So the rhythm was wrong.
Exactly. Then they moved to electromagnetic forces. We know the magnetar possesses a 10 to the 14 gas magnetic field. Could the magnetic field itself physically grab the ionized plasma disk and twist it, forcing it to precess?
Given how strong that field is, it seems highly probable that magnetic torque could push a plasma disk around.
Magnetic torque is a powerful force, and it absolutely interacts with the disk. But again, the physics of magnetic torque has a different mathematical dependency on the distance from the star. A wobble driven purely by the magnetic field produced a rhythm that simply did not fit the light curve. No matter how they adjusted the variables for classical gravity, magnetic torque, or even exotic gas collision models, the resulting simulated light curves failed to reproduce the precise timing of those 4 accelerating bumps.
The alternative puzzle pieces just refused to fit the lock.
Yes. Only one mechanism fit the data. Only Einstein's lens-stirring precession, driven by a rapidly spinning ultra-dense central mass, matched the timing of the chirp perfectly.
Which leads to a thrilling conclusion. If general relativity is the only mathematical framework that reproduces the observation, then the physical parameters required by that relativistic model must be real. By measuring the exact timing of the wobble, the team essentially reverse-engineered Einstein's equations to calculate the precise physical statistics of the unseen object at the center of the debris. What were the exact numbers they extracted from the space-time drag?
The derived parameters were astonishing. By quantifying exactly how fast the local spacetime was being dragged to produce the observed chirp, they calculated that the newly born neutron star at the center of SN 2024 FAV is spinning with a period of precisely 4.2 milliseconds.
Wait, 4.2 milliseconds. Let me do the math on that. That means this object is completing a full 360-degree rotation, roughly 238 times every single second.
Correct. A sphere 10 miles wide, containing the mass of a sun, rotating 238 times a second. But the calculations for the magnetic field, derived from the spin-down rate required to power the overall luminosity, were even more extreme. The precessional math and energy budget required the central object to possess a magnetic field roughly 300 trillion times stronger than Earth's.
300 trillion. Let's just sit with the magnitude of that number. Earth's magnetic field is robust enough to deflect the solar wind, to protect our atmosphere from being stripped away into space, to align compass needles all over the globe. And you take that planetary force, multiply it by 300 trillion.
It's almost unimaginable.
It really is. The sheer violent electromagnetic energy required to sustain a field that strong, it's a physical extreme that almost defies description.
And crucially, both of those derived numbers, the 4.2 millisecond spin period and the 3 times 10 to the 14 Gauss magnetic field, are the absolute defining theoretical characteristics of a magnetar.
Here's where it gets really interesting. When you synthesize the entire picture, the sustained superluminous energy output that defies nickel-56 decay, the accelerating rhythmic bumps in the light curve, the rigorous mathematical necessity of relativistic frame dragging, and the final calculated parameters of the central object, it all points to one inescapable conclusion. Alex Filipenko and Andy Howell, the senior astronomers overseeing the project, stated definitively that this observation is the smoking gun.
It is the definitive proof the field has been waiting for. It ties the observational data directly to the theoretical framework. The 2010 model proposed by Kazin, Bilston, and Woosley was correct. The hidden engine is no longer hidden.
The magic trick is revealed?
Exactly. The relativistic chirp in the supernova signal was the physical equivalent of pulling back the plasma curtain and revealing the exact machinery of the magic trick. Joseph Farah's analytical work demonstrated, beyond a shadow of a doubt, that a magnetar was birthed in the core of this superluminous supernova and that its furious spin and immense magnetic field are exactly what kept the explosion glowing.
It's just a triumphant moment for theoretical physics. You derive a model on a chalkboard, you wait 16 years, and the universe eventually provides the exact receipts. But, as with all great paradigm shifts in science, answering one massive question immediately opens the door to a dozen new complications. We have definitively solved the mystery of the central engine for SN 2024 AFAV. But we have to look at the broader landscape of transient astronomy. Does the single smoking gun mean the case is permanently closed? Does a newborn magnetar explain every single superluminous supernova we've ever cataloged?
No. And the researchers involved are very careful to delineate that. The universe is incredibly diverse, and astrophysical phenomena often exhibit what we call degeneracy, meaning multiple different physical mechanisms can produce a similar observational result.
So it could be different engines for different stars.
Precisely. The magnetar model is now proven reality for SN 2024 AFAV, and it likely accounts for a significant majority of type I hydrogen-poor superluminous events. But it does not universally explain all of them. There are alternative engines that must be applied to different subclasses of supernovae.
What other invisible mechanisms could be generating that much energy?
We discussed circumstellar interaction earlier, the supernova shockwave crashing into pre-existing shells of gas. While we mathematically proved that couldn't explain the 4 accelerating bumps in this specific event, there's a whole class of type II superluminous supernovae which are rich in hydrogen, where the sustained brightness is almost certainly powered by that exact mechanism.
Ah, okay.
In those cases, the progenitor star was likely a luminous blue variable that shed massive amounts of material before dying. The engine isn't a spinning magnetic core, it's the continuous kinetic friction of the debris field plowing into an incredibly dense, extended nebula.
So kinetic shockwaves are still a valid engine for certain types of explosions. Are there any other theoretical engines that utilize a central compact object, but perhaps not a magnetar?
Yes. Dan Kazin, the theorist who helped pioneer the magnetar model, has heavily researched another fascinating and perhaps even more violent possibility known as the collapsor model.
The collapsor model.
Right. What if the progenitor star is so exceptionally massive that when its iron core collapses, the crush of gravity completely overpowers the neutron degeneracy pressure? The core doesn't stop at a neutron star, it collapses directly into a black hole.
A newborn black hole operating at the exact center of the supernova.
Exactly. In the collapsor scenario, you also have massive amounts of stellar material falling back inward. That material forms a dense accretion disk swirling around the newly formed black hole. The friction in that disk generates immense heat, and the magnetic fields within the disk can launch relativistic jets of energy outward, piercing through the star and powering a superluminous explosion. And crucially, a spinning black hole also drags spacetime.
Oh. So a tilted accretion disk around a black hole would also undergo lens-Thirring precession.
Yes, it would also wobble, and it could theoretically produce similar rhythmic bumps in a light curve. However, because a black hole is more massive than a neutron star, the precessional mathematics would be different. The timing of the chirp would have a different signature.
So the engine could be a spinning magnetar, or it could be a baby black hole voraciously consuming its own stellar debris, and the only way to tell them apart is to analyze the precise rhythm of the wobble.
That is exactly where the field is heading. The landscape of astrophysics has fundamentally shifted because of this single observation. Prior to SN 2024 AFAV, there was a heavy reliance on circumstellar gas collisions to explain many of these ultra-bright transients. But as Filipenko noted, this discovery proves that central engines account for a much larger fraction of these events than previously accepted.
That makes sense.
Yeah, the magnetar model has graduated from an elegant hypothesis to a confirmed operational mechanism.
And it feels like we are standing on the precipice of a massive explosion in data. If you know exactly what to look for, if you know that you need to listen for a relativistic chirp to identify an engine, you can start tuning your algorithms to find it. And the timing for this realization is perfect because the astronomical community is about to bring some incredible new observational tools online. I'm thinking specifically of the Vera C. Rubin Observatory.
Oh, absolutely. The Vera C. Rubin Observatory is poised to fundamentally revolutionize time-domain astronomy. Currently under construction in Chile, it is designed to conduct the legacy survey of space and time, which is an unprecedented decade-long optical survey. It features an 8.4-meter mirror and a 3,200 megapixel camera, giving it an immense field of view.
3,200 megapixels, that's absurd.
It is. It will be able to photograph the entire visible southern sky every few nights.
Which means it isn't just taking deep space portraits. It is essentially filming a high-resolution movie of the cosmos. It is going to catch everything that flashes, moves, or changes brightness.
The data volume will be staggering. The sheer number of transient events, things that appear and disappear like supernovae, tidal disruption events, and kilonovae, that the Rubin Observatory will detect will require entirely new machine learning pipelines to process.
I can imagine.
Right now, humanity discovers a few thousand supernovae a year. The Rubin Observatory is expected to flag millions of transients every single year.
Millions. And buried in those massive data sets will undoubtedly be hundreds, perhaps thousands, of superluminous supernovae. And because Rubin will be imaging the sky so frequently, we won't just get partial snapshots, we will have incredibly detailed, high-resolution, continuous light curves for a vast population of them.
That is the crucial point. Joseph Farah anticipates that once the Rubin Observatory is operational, astronomers are going to discover many, many more of these chirping supernovae. We are going to transition from studying single rare events to performing population statistics.
Which changes everything.
Entirely. We will be able to categorize them, measure their spin rates, calculate their magnetic fields, and definitively distinguish the magnetar engines from the black hole collapsor engines based purely on the nuanced mathematics of their space-time wobbles. We are opening up a whole new subfield of observational astrophysics. We are moving from simply documenting the glow of stellar explosions to actively reverse engineering the relativistic engines hidden inside them.
It is staggering to look back at the arc of this scientific journey. Just to summarize the sheer scale of what we've discussed today, we started with a persistent 16-year anomaly where the thermodynamic math of dying stars refused to balance. We explored how theoretical physicists essentially invented an invisible magic trick, a spinning magnetic dynamo to balance the equations.
The trick that turned out to be real.
Right. We then cast our gaze across 1 billion light years of intergalactic space, utilizing a global network of robotic telescopes to track a single explosion for 200 days, only to find a light curve that chirped. And to finally decode that chirp, we had to rely on Albert Einstein's profound, century-old realization that a spinning, city-sized, ultra-dense core can physically grab the fabric of space and time and drag it into a wobbling cosmic lighthouse.
It is a profound testament to both the power of human curiosity and the rigorous predictive power of the scientific method. But I think the most poignant and humbling takeaway comes directly from Joseph Farah, the researcher who first recognized the significance of the chirp.
What did he say?
When reflecting on the implications of this discovery, he said, "It's the universe telling us out loud and in our face that we don't fully understand it yet and challenging us to explain it."
Oh, I love that perspective. The universe throwing down a gauntlet. It's a constant reminder that no matter how sophisticated our models become, the cosmos is always capable of surprising us. It is always ready to reveal engines and relativistic mechanisms that are far more complex, beautiful, and violent than our initial theories imagine.
It forces humility upon the field, but it also drives relentless progress. Every time we solve one of these macroscopic mysteries, we peel back a layer of reality, only to find deeper, more intricate physics operating underneath.
Layers within layers.
Exactly. The fact that the space-time dragging predicted by Einstein on a chalkboard in 1918 is strictly required to understand the rhythmic flashing of a dying star a billion light years away in 2024, it demonstrates that the underlying rules of the universe are profoundly and beautifully interconnected.
So what does this all mean for you? The next time you step outside on a clear, dark night, I want you to look up at the stars. But don't just focus on the points of light. Look at the vast, dark patches of space between them. And consider this final thought. If these hidden magnetars are spinning 200 times a second and violently dragging the geometry of space-time, they aren't just emitting light, they are likely generating intense ripples in gravity itself.
Oh, gravitational waves, yes.
Yeah, the next generation of gravitational wave detectors might not just see the afterglow of these explosions. We might actually be able to feel the fabric of the universe vibrate as that infant star takes its first furious spin in the dark.
A fascinating prospect to consider.
Just waiting for us to finally learn how to listen.